So lately we've just been doing some work on Lewis structures, and I gave you some from some recent NCEA questions. I'm going to go through some of those now, just a few of them. So one of the ones that you said you'd like me to go through is xenon tetrafluoride. So XeF4. And the first thing that we see on this one that's a bit weird is that it's xenon, which is a noble gas, which we've been told are inert, so don't react. Fluorine has got such a high electronegativity, and xenon's outermost electrons are so far away from the nucleus that actually we can have some bonding occur here. Alright, so that's sort of why this can form. We still follow the same rules, so we look at how many valence electrons. Xenon's a noble gas, so it's got 8, and we've got 4 times 7, because you've got 4 fluorine atoms which are in group 17. So 4 times 7 is 28, plus 8 is 36 electrons in total. Xenon's going to be our central atom. This is where it sort of breaks that little rule I said about valency. So its valency would be 0, or it could be 8. So that's why it's going in the middle. So here we go. We're going to put xenon in the middle of this one. And just like before, we're going to fill in the fluorines around it. Easiest way to do it is to go top, left, right, bottom. And then we're going to fill in the electron clouds around the fluorines to make sure they obey the octet rule. Because they're peripheral or outside atoms, they've got to obey the octet rule. So here we go. Now this structure here, I can see quickly there's 4 times 8, because each bond is 2 electrons. There's 4 times 8 is 32 electrons in this. So I need to put in 4 more. They need to be paired up, and they cannot go on one of the outside atoms. So in this case, xenon is going to have 2 more pairs. Put them opposite each other because the lone pairs of electrons, they're likely to repel each other, so they'll be as far away as possible. It's not wrong to have them there and there though, because in 3 dimensions, they'd still be opposite each other. And we'll do that when we look at shapes, which is later in this lesson, but not in this video. So xenon tetrafluoride would have this Lewis structure. Or as I say, it would be equally correct to move that lone pair there or there if you wanted to. Right, the next one that you identified was an ion, BrF4 negative. So again, we're going to follow that same rule with counting the number of electrons. Bromine is 7, being in group 17. Each fluorine is 7, being in group 17. And because of the negative charge, I'm going to add 1 more. So I'm going to end up again with 36 electrons like I have in xenon tetrafluoride. So it's actually going to look exactly the same. I've got 5 atoms, I've got 36 electrons, I've got 36 electrons. They're going to look exactly the same. Bromine in the middle. 4 fluorines around it. Fill in the electron clouds. And there's 32, so 2 more electrons there, 2 more electrons there. Nearly done. Because it's an ion, I have 1 more step to do. Square bracket here, and a negative charge. And then I'm done with that one. So it is actually incredibly similar to this one. And when we do shapes, we're going to find they are the same shape. The next one that you identified was AsF5. So arsenic pentafluoride. Now arsenic is below phosphorus, which is below nitrogen in group 15. So it means that it's got 5 valence electrons. It's above our little imaginary line that we have that sort of goes from boron down to At. So we can be pretty confident that it's going to have 5 electrons involved in bonding because it's above that imaginary line. Then we've got 5 times fluorine, which is in group 17, so it has 7. So we have a total of 40 electrons. Just quickly check my maths. Yeah. Again, arsenic is going to go in the middle because it's got the highest valency. Its valency is 3. Fluorine's valency is only 1. And I'm going to put those 5 around it. Now, you don't know if it's going to be lone pairs of electrons around the arsenic yet, just by looking at it. So I'm going to pretend that it's going to spread them out as evenly as possible. So on a 2-dimension surface, for me to see them as far away apart as possible, I'm going to make it like the points of a pentagon. Fluorine, 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 fluorine. Fill in the electron clouds. And 5 times 8 is indeed 40. So that's correct, so I stop. So that's going to be its lowest structure. It doesn't need lone pairs around the arsenic. That's complete. The last one is one that I chose just because I know it's a little bit different to these ones. Not grossly different, but it is a little different. And that's chlorine trifluoride. So Cl(F)3. And here I've got 7 plus 3 times 7 is 28 electrons. Chlorine is further down the periodic table, so I know it's going to be the central atom in this case because the valency of both of them is 1. So chlorine in the middle. And again, I don't know how many lone pairs are going to be there, but we're not going to have any double bonds. So I'm going to put the fluorines like that, expecting there to be a lone pair of electrons down here. Fill in the fluorines, lone pairs. And I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So I've got 4 more electrons to put in there. Now, normally I'd get really confused here, but there's only one space. It's got to obey the octet rule. It doesn't. As it's the central atom, I'm allowed to break the octet rule. I'm actually going to put them like that. But it doesn't matter if you put them there and there, there and there, whatever. One centrally and one there, it doesn't matter where you put them. It's a Lewis structure showing you basically where the electrons are found around which atoms and which chemical bonds are present. It doesn't matter about shape yet. Lewis structures are not used to tell us shape. They're used to predict shape, which is what we're going to do later today.